Okay, hello. Last talk, I hope last but not least. So, I don't know, Kevin might want to comment on that. This thing says validation, but really it should say it's a check. It's a check on accuracy. And in this case, it's looking at fire-induced flows through doorways in a room which has a small fire on the floor. And so the two authors beside myself that are not listed in the program are Li Wang. He's from the China University of Mining and Technology, and he tells me that he's watching this now via the internet. So Li, if you're watching, hello. The other author is Johnson Lim, and he's from Singapore. And you can see he's from the Defense Science and Technology Agency. Both of these people passed through the University of Maryland. Lim recently did his master's study, and he used FDS to do a very careful analysis of balcony spill plumes, working mainly off the data of Spearpoint, and the other author, where's Spearpoint? Harris. So very good experimental work, and a topic of a lot of controversy because of the design of smoke ventilation systems in shopping malls. And Lei came to me as a PhD student from his university, designed to do some work at our place and parlay that into a PhD, which he did, and now he's a lecturer at that university. And his topic that we decided to look at was to look at these fire-induced flows. Well, here we can just skip that. And this is the experimental setup that we focused on. Data taken a long time ago by myself and Bill Rankinen and Ken Steckler. In recent years, Margaret Law, who some of you may know, particularly those from Arup, correlated this data using Q star. Not all of the data, but some of it, and she was always curious about why it worked. So Lei and I undertook an analysis, an algebraic analysis, using a zone model formulation to see why it worked. And we came up with an explanation, and in that we developed a correlation as well. That's a very simple correlation that can be used if you know the temperature in the room and some idea of where the fire is. Because where the fire is affected entrainment, and there's a little factor in there for that. These are publications in the Fire Safety Journal, so if anyone's interested, they can look them up. Now, these experiments were designed to get very good data on the mass flow rate into and out of a room when there's a fire, because one needs to understand the airflow dynamics in such fires. And the original theory was put out by Kawagoe for fully developed fires that have a uniform temperature inside, but early fires don't have that. So we know that there's a layer. And these experiments used very good instrumentation. We used the bidirectional probe in a doorway. The burner itself was a circular burner, and it was fit flush on the floor. So it wasn't raised, there wasn't any tripping over it. The floor was raised, and the burner sat on the floor. The thermocouples were not ordinary thermocouples. They were aspirated thermocouples to correct for any radiation error. Because in any fire experiment, you have a radiation error. And if you just look at the thermocouple data and compare with some model, you better correct the data first if you're looking at temperature. So these were aspirated probes to give us a good measurement of what the heck the temperature was. And the bidirectional probes were also calibrated too, because they depend on the Reynolds number or the flow rate. If you get too low in flow, that factor in there that's like a Bernoulli factor changes with the Reynolds number. So you have to know that when you execute all of this. And these were steady state experiments where mainly Bill Rankinen and Ken Steckler moved this trolley over the vent and made these measurements. And what we were really looking at is flow rates. And our criteria for saying that we got a good answer was that we got a mass balance between in and out. And the flow distribution over this field, it's not uniform across the width. There's some bumps in it. And these bumps are actually calculated by Howard Bauman in inviscid model. So this flow through the door is almost inviscid Bernoulli flow. And if you know the temperature on both sides, that's what these experiments basically proved. If you know the temperature distribution on both sides of the opening and the flow coefficient for the opening, you can predict the flow quite accurately. These data have been used to sort of validate many field models over the period. Most of them are RANTs. And so FDS is sort of taken over, I think, from RANTs. And in the validation guide, I see that there is a check against these data on the center line for velocity. So in our analysis, we went a little further. We were mainly interested in the flow rate. This work was done by Lee. First, we did these algebraic models and were motivated by Margaret Law's correlation. And then Lee said, like a new student, I want to use FDS. I said, okay, it should do a good job. And he ran it, and this is a plot of mass flow rate for the burner in the center at a given energy flow rate, and you see it's the width of the opening. So each point on there represents one configuration, a door size, so a door width, and a given fire size inside, and they're all basically steady state measurements. And so the black dots on the top is the experimental results. And now FDS is predicting the blue line. So we were kind of disappointed and a little surprised. And so I looked in the FDS guide and the criteria, and I looked at the boundary conditions. Now the way Lay ran this is he just used the vent conditions in the code. So he stopped the domain of the code right at the face of the vent and used those pressure boundary conditions, which I believe, you guys can correct me, is the dynamic pressure is 0 top and bottom, flow out and flow in. Now I went back and I looked at Bernoulli, and it looked to me like it's okay for it coming in, but going out, it's not that. It's something else. And I don't know if that's I don't have an expression there, but we have put an expression in our paper in Fire Safety Journal. So maybe that's the reason. In any case, when Johnson Lim did his work, and it was such a nice, careful piece of work for the balcony spill, I kind of challenged him. And I said, why don't you try the doorway flow and use the same kind of intensity and passion for that? And so he went off to Singapore and he contacted Lay, and they teamed up and they did this work. And I'm their spokesperson. So I hope I'm conveying it accurately and properly. So the first work that Lay did, he put 5 cells across the face of the burner. This is a 30-centimeter burner. And when they redid it, I think they put 6 cells across. So it's a 5-centimeter cell size, and I think it's the same as you use in the guide, in the validation guide. So that was okay. But now, instead of using the vent condition, what they did is they went outside. And so they moved this and they checked progressively when they got their mass flow rate to within 5%. And so they're hoping to kind of establish a rule of thumb. If you move it this far out, you might get good results for the mass flow rate. The other thing they did is, it's a square burner. Now maybe you can make these cells up so that it looks a little bit like a round burner. But in these experiments, we put the burner against the wall, and it was a round burner. So it doesn't fit tight against the wall. So when you put a square burner against the wall, you cut off one side. If you put it in a corner, you're cutting off 2 sides. So it's not modeling the round burner. So what they did to affect this is to move the burner away from the wall to give it a chance to entrain around the sides. And then they did that to a certain distance where they got good mass flow results. So that's the way they operated. And they also corrected a little bit for radiation. I think they initially used the default value for radiation fraction. Then they went back, hey, this is a methane burner. We should probably use a lower fraction, and they put that in, and then they ran it. So this is the finer resolution, and that's what they chose. Let's see what this says. They actually went down to 2.5, and they didn't see any difference. So they were playing in this thing to really try to get the thing to work. So they suggested it wasn't grid dependent after that, so they stuck to 5. Radiation fraction, like they said, they kind of got that, matched it to the real fire, not used the default value. And then this is what they did. They extended the domain out, and they used a factor that was this d sub d, kind of an effective distance or effective diameter based on the area of the vent. So that was their model. And they did this for all the vent cases because this is a doorway shrinking down to smaller and smaller widths. So it's over a whole range. And so they found that if they extended it out 0.5, half of that, they got good results. And so let me show you the results that they got. Now, we didn't only look at mass flow rate. We looked at, is it getting the neutral plane right? So those are numbers that are not so arbitrary. Those are parameters not so arbitrary. The other two are a little bit. It's the average lower layer temperature, and it's the smoke layer height. Now, those depend on how you're defining them. When we did the work in Ken Steckler's experiments, we had an algorithm for that. I don't know if you use the same one in FDS. If you don't, then we're inconsistent, and that could explain why there's differences on looking at those parameters. So, all right, and this was the other approach, shifting the thing away from the wall, and they found that if you move it 2 burner diameters away, then mass flow rate, good results. So here's the results. Again, the black squares are the data. This is for the burner in the center. And these experiments were at several burning rates. So they obviously picked one, and I forgot what that is. But there was a range of fire sizes as well that one could also look at. And you see the previous FDS was low, as you saw in the first slide, and now it does a really good job. This is now looking at the lower layer temperature. Now, you might say, well, the lower layer temperature should be ambient. No, it's not. The floor is getting hot, and when this flow comes into the opening, particularly as you make the width more and more narrow, the layer in the room goes down, and the neutral plane is up here. So when that flow comes in, it has to go through some of the hot stuff before it goes down. And so it carries some of that with it. And that probably accounts for most of why that layer is getting hot down at the bottom. And you could see, oops, sorry. I meant to do this. Does it work? You could see, people say, zone model, it's no good. But look at the kind of temperature distributions that you get. This is in the gas phase, and this is the walls. So, reasonable. Now, this is lower layer temperature. You see there's still some difference. All right? And again, it could be due to the criteria. I don't know if we're using the same one. Here's the neutral plane. Now the neutral plane is a little bit lower. Not so bad, but a little bit lower over these experiments. Now you might say, why isn't there like a nice smooth curve? The reason is these experiments were done off-site in a building that wasn't heated. And we did the experiments in the heat of the summer and in the cold of the winter. Mostly I didn't go out there. I sent Ken Steckler, who was the research associate, and Bill Renkinen, who was the technician, because there was finer work for me to do in my office, you see. But actually, we built this facility with our own hands, and they executed most of this work. And so those dips in the curves are due to the change in ambient temperature that's driving this flow as well, because it's buoyancy driven. And so here you see the smoke layer height, and again, the differences. And now, you know, we could look at the results for the burner in the corner, and you could see by, you know, moving it away, good results are achieved between their current runs compared to the previous runs. And again, differences with the lower layer and the smoke layer height, and the same if you put the burner on the wall. So in essence, you could say that I mean, this kind of summarizes the results, but you get a sort of a feeling for it. In essence, they got two rules of thumb. If you want to model the vent properly, you have to put this domain outside the vent, and they're giving you a criteria for this that might be general or might be not, but you got to put it outside the vent, it appears. Their grid size in between the two cases were not that different, so I don't think it's due to that. It's undoubtedly due to putting this thing outside. And the other thing is, if you have a fire against the wall, you know, and it's a round burner, you better not make it a square burner in FDS. And some of these are maybe logical, but when you're running the code as a first-time user or even an old-time user, you may not think about these little subtleties. So this is the essence of the work. I hope that I've presented it in a good way for these two guys. They are submitting it to a journal, so perhaps it'll be peer-reviewed someday and in print. So I thank you very much.
Any questions for Jim? Time to get even.
I would suggest when you look at this kind of compartment data that you just plot the profiles directly. And one of the things I don't actually like to do with FDS results is use this layer reduction formula. I mean, it's something that we do when we compare with the zone models that the NRC uses,
right.
But I much prefer to just simply plot the profiles, and you
The
have
temperature profile.
the temperature and velocity profiles.
Yeah. That
because
was
then you'll see if there's any problem.
This is a job for the validation guy.
Well, it's in the that's the way we plot it in the validation guide. We don't even compute
No, but you
these
didn't.
layer
In the
heights and so
validation
forth.
guide, you only show the center line temperature, center line velocities. So I didn't see that you went beyond that.
Yeah, I just to keep the number of plots down to a reasonable number. We could add them. When we looked at the velocity plots, we didn't see serious problems, so we just looked at the center line. It would be easy enough to look at off center line. But the point I'm trying to make is just look at these profiles rather than these so-called the zone model type parameters.
In view of this discussion we're having, I mean, like you just said, it would be nice to show the temperature profile along with the velocity profile in the door and in the room.
Right. Yeah. We have it in the room and then in the door, the profiles.
All right.
Yeah.
Put it in the guide. That would be very good.
It's in there. The center lines profile
I
in the
didn't
door.
I didn't see temperature, Kevin. I only saw velocity. But I could
Because you were in the wrong chapter. The temperature is in a separate chapter because we divide the data up into different chapters.
All right.
Velocity in one chapter, and then there's temperature in another.
You'll have to school me better.
All right, I'll show you.
Thanks, Kevin. Anybody else have a question for Jim?
We have one comment from the web
Wow.
that wondering what material values were chosen in the FDS model runs for walls and flooring and ceilings, how it was absorbing energy.
Well, it was whatever the room was made out of, and that's what they put in.
I'm assuming it would be
I
on the
don't
paper.
think I don't think it was gypsum board. It was some inert material that we bought at the time, and that's what they used. To the best of their ability, that's what they put in.
And I'm assuming it's documented
Yeah,
in the
yeah.
paper as well. So
Yes.
Okay, thank you.
All right. Well, thanks again, Jim.